Good afternoon, one and all. This is Aparna, Assistant Professor, ECE Department, MS Raju Institute of Technology, Autonomous, Visakhapatnam. In this session, we are going to explain you about the VI characteristics of a PN junction diode. By the end of this session, you will be able to know the basic difference between VI and IV characteristics of an electronic device, and particularly, we will learn something more about the VI characteristics of a PN junction diode. See, before entering into the topic, let me recall what are the characteristics of a graph. Graph is nothing but it is a pictorial representation. If you observe the pictorial representation of any component or device, you will observe the following parameters: domain, and the domain, what is the working area, range, active region, maximum value, minimum value, and zero at the origin, and what is the y-intercept, and what is the time interval of increment of that particular parameter value, and what is the region of decrement of that particular value. And what is VI characteristic? V stands for voltage or potential. We can also call it as potential, and I stands for characteristic, current. VI characteristic means, as the name itself indicates, this characteristic gives us an idea about the voltage that we are applying to that particular device, and I will give us an idea about how much amount of current is flowing through that particular device. VI graph. As I already told you, graph is a pictorial representation. So it is a pictorial representation which gives us an idea about the variations in the applied voltage and the current flowing through that particular device. And what is the use of deriving this VI characteristics for a particular device? By observing the VI characteristics of a particular device, we can identify the working region or operating point or threshold point of a particular device. And what are the different types of VI graphs available? VI characteristics are basically of two types: linear VI characteristics and non-linear VI characteristics. Linear VI characteristic means if you observe the curve, you will observe a constant slope, and as a result, a constant resistance will be there. Non-linear characteristic means you will observe some variations. The slope of the curve will give us an idea about the resistance value. You will observe a curve. And we can come to know about the VI characteristics of one of a rectifier known as SCR, silicon controlled rectifier. And we will be able to understand the VI characteristics of a PN junction diode, which is an electronic device. And what are the conditions of VI characteristics when it is zero bias? That means when no biasing is given to the device, and when the diode is forward biased, as well as when the diode is reverse biased. And we will come to know the VI characteristics of a special type of diode known as Gina diode. And what is the basic difference between VI characteristics and IV characteristics? In the case of VI characteristics, we consider voltage or potential at x-axis and current at y-axis, and the slope of the curve will give us an idea about the resistance value. In IV graph, we take potential at y-axis and current at x-axis. So the reciprocal of the curve IV graph will give us the resistance value. This is the graphical representation of voltage and the current variations through a PN junction diode. If you keenly observe the diagram, as these are VI characteristics, according to the concept given to you, voltage is considered on the x-axis and current will be taken on y-axis. And here you will observe two regions, forward region and reverse region. And you will observe two dotted lines, namely forward voltage and reverse breakdown voltage. And you will observe forward current as well as reverse leakage current. Forward bias condition means, in the forward bias condition, forward biasing means positive terminal of the battery and the anode of the diode are connected. And negative terminal of the battery is given to the cathode terminal of the diode. Then we can say that the diode is forward biased. In the forward biased condition, after keep on increasing the applied voltage, initially there will be no current in the circuit. If we keep on increasing the externally applied voltage, after crossing a particular value, the current starts to flow through the device as well as through the circuit. So the value from where the current starts to flow is known as the breakdown value or threshold value or operating value of that particular device. This operating voltage value or biasing voltage, we can also call it as biasing voltage. So biasing voltage for a germanium diode is 0.3 volts, whereas for silicon, the biasing voltage is 0.7 volts. It means that after crossing the 0.3 volts value only, germanium diodes start conducting. And after crossing 0.7 volts only, silicon diodes starts to conduct current, starts to allow current to pass through it. What happens when a diode is forward biased? That means we are giving some external voltage to the diode. When we are giving some external voltage, the charge carriers inside the semiconducting material, inside the diode, they get excited and they start to move. As a result, the majority carriers, charge carriers, holes in the p-type region, they start to flow towards the n-type region, and the majority carriers, which are nothing but electrons of the n-type, they start to travel from n region to p region of the diode. As a result, there exists a movement in the charge carriers, which is nothing but the formation of current. We will consider the flow of charge carriers as current. So current starts to flow. So by observing the graph, we can come to know from which value of the voltage diode starts to conduct. That value is considered as threshold voltage. So when a diode is forward biased, what happens actually inside the diode? At the junction, always there exists some potential barrier, or we call that layer as depletion layer. When a diode is forward biased, when the charge carriers, they travel towards the junction, as a result, at a particular instant, the length of the depletion layer gets very much reduced, and finally, the width of the depletion layer becomes very thin, and at a particular value, the junction breaks down, and the charge carriers, they travel completely. They can they can induce in the N region from the P region. So the charge carriers which start to travel from the P region, they can reach the N region, and as a result, whole electron combination occurs. Once the potential barrier is crossed, the barrier voltage or threshold voltage is crossed, the current starts to conduct in the device as well as in the circuit. What happens if the polarity of the devices change? That means the anode terminal is given to the negative terminal of the battery and cathode terminal of the device is given to the positive terminal of the battery, what happens? When we give some voltage in the reverse biased condition at a particular value, what happens? As we keep on increasing the voltage in the reverse biased condition, the charge carriers, instead of traveling towards the junction, they start to travel away from the junction and towards the battery terminal, they will start to move. As a result, the width of the depletion region increases drastically, and completely there will be blockage of current to through the diode as well as in the circuit. So we can say that current will be allowed through a diode only when it is forward biased condition, and the diode blocks the flow of current when it is reverse biased. What is the importance of VI characteristics? As we seen in the previous slides, we can come to know about the importance of VI characteristics. So by observing the VI characteristic, the graphical representation of variations of voltage and current, we can come to know about the operating point or threshold point of that particular component. And when we come to know about the features of VI graph, two statements can be given. One is voltage is directly proportional to current, and voltage is also directly proportional to resistance also. So there is a linear relationship between voltage and current. V is directly proportional to I, and we can say that V is directly proportional to resistance also. The slope of the curve gives us about the resistance value. So we can say that voltage is directly not only directly proportional to electric current, but also it is directly proportional to resistance. And by the end of this session, I think you can answer the short answer questions. What is the difference between germanium and silicon diodes? Both are the frequently used materials for the diodes, and the main difference occurs in their operating point or a threshold point or a quotient point. For germanium, the operating point is 0.3 volts, whereas for silicon diodes, the operating point is 0.7 volts. And like this, you can answer these simple short answer questions. And I want to answer one more question for your convenience. What are the factors governing the reverse saturation current in a PN junction diode? Let me give you a brief introduction regarding this reverse saturation current means. Here you will observe in the reverse biased condition, when you keep on increasing the voltage, after crossing the reverse breakdown voltage, there exists some current known as reverse saturation current. And along with that reverse saturation current, we will observe one more current, reverse leakage current. What is this reverse leakage current? Reverse leakage current means the current that flows from the depletion layer when the diode is in the reverse biased condition. That current is known as reverse leakage current. In the next session, we will come to know about the effect of temperature on the VI characteristics of a PN junction diode. Temperature dependence on the VI characteristics. I hope you got some idea regarding the VI characteristics of a PN junction diode. Thank you.